So now, what is optimization? Okay, so this course is about optimization method. So we just have to focus on methods in finding the solution of optimization. So what is optimization? Anyone knows about the definition of optimization? Can anyone share some thoughts of yours? Anyone? This is just a definition of the optimization, but have you heard about this before? What is optimization? So on.
Yes, doctor.
What?
Mic test.
Finding?
Mic test.
Sorry?
Mic test. Mic test.
I can't hear you.
Mic test. Mic test. Can doctor hear me?
Yes.
Yes. Good morning, doctor.
Okay.
I think we have heard of optimization method before this, but it's like x plus y equals to 100. So we have to find out what is x and what is y to make sure that it is optimized, like how much product we have to use for x, how much product we have to use for y, so that we can maximize the profit and also minimize the losses. That's what we have learned through optimization before this.
All right, good. Okay. So Shifa said finding the best solution, and Rachel said finding the best value of x and y to optimize the value so that we want to maximize the profit and minimize the loss. So basically, in terms of profit and loss, that is the idea of the optimization, right? Okay. So for now, as you can see from the definition here, optimization is the act of obtaining the best result. Okay. So what kind of result? Okay, in terms of profit and loss, in terms of production, in terms of reducing the defect item and so on. Right. So the ultimate goal of any decision is to either minimize the effort required or maximize the desired benefit. So that benefit can either be profit, can either be production, can either be the best rate, and so on. Okay, so now, so since the effort required or the benefit desired in any practical situation can be expressed as a function of certain decision variables, so mathematically, all of this desired can be expressed as a function, okay, of a certain decision variables. Then optimization can be defined as the process of finding the condition that give the maximum and minimum value of a function. So you know, as a layman term, you know the definition of optimization. And then mathematically, you convert that problem to a function, okay, of certain variables. And then this optimization can be defined as finding the condition that give the maximum and minimum value of a function. So mathematically, we're going to use function. So this type of problem is called unconstrained optimization problem. What type of problem? This type. So if you just have a function, you want to maximize that function where x is in x, then this is just an example of unconstrained optimization. What about the constraint optimization? So the constraint optimization, of course, we have certain types of constraint. So the mathematical programming techniques are also useful in finding the minimum or maximum of a function of several variables under a prescribed set of constraints. So if we have another function defined to the function that you want to maximize or minimize, we call it as a constraint optimization problem. Okay, clear. Can you see the difference between unconstrained and constrained optimization? Okay. So now fx here is an objective function, gix here constraint, and the g function can either be linear or nonlinear. So the difference is here. We just have constraint for constraint optimization. We have no constraint for unconstrained optimization. But the idea is always the same. We want to find the maximum and minimum value of a function. Okay. So where can we apply all of this optimization? There are a lot of optimization application. We want to optimum design of electrical networks, selection of sites for industry, design of water resources, allocation of resources. Okay, we just like your friend said, we want to maximize the profit. We want to maximize the production. Okay, we want to sometimes this optimization can also be applied to image processing. We want to maximize the blur, we want to minimize the blur image so that the image can be clearer. So all of those things comes from the optimization algorithm. But which methods that we're going to use? Okay, because there are a lot of methods. So that's why we're going to find the best methods. So before we find the best method, of course, we need to understand each of the methods that we're going to discuss. Okay, clear? Any question regarding this?
No questions, Doctor.
Okay, so can anyone give me another application of optimization that you can see those kind of application use optimization concept? Okay, can I get 3 of application from you? You have about 62 participants, right? How many participants? 60 participants, including me, so 59. Okay, any application that crossed to your mind right now? I gave you some examples already.
Doctor. I can give one come in mind when regarding the optimization, which is transportation. Transportation involving the process of sourcing, getting the product, and then getting the product transported to the place. Can use the optimization method.
Yes, okay, thank you. May I know who are you?
Sha'ada.
Shahada, all right. Okay, another one. At least 3. We have one already. Transportation, of course, we want to maybe in terms of waiting time, we want to minimize the waiting time of transportation problem from A to B. For airplane implementation, we want to minimize the waiting time so that we can maximize the profit. That's the idea of optimization also. In terms of, maybe in terms of diet, you can choose the best solution to minimize the protein intake, the carbohydrate intake, so that we can match to the weight or height and so on. So that's another thing in optimization. There's a lot of application in optimization. Okay, in industry, of course, there are usage of optimization, but sometimes if you are approaching to the industry, some industrial practitioner use some sort of system already. So the design system where they just can optimize their production. Okay, but those system comes from this optimization method. The fundamental comes from the optimization. The fundamental comes from the operation research. All of the theorems, all of the theories start with that. Okay. Another two? Are you still waiting? Okay, Karian, financial department. Okay, of course, to maximize the profit. Okay, the last one. I gave you a lot already, right? No one? Okay, this one is the last one. Thank you, Yijia. Schedule optimization, arranging timetable of manpower and so on. Okay, good. Okay, so now you can see that this optimization are very applicable in the real life. So that's why it is important for you to understand the methods first. Okay, so let's take a look. Next one. So now basic theories. Okay, so what are the theories or the fundamental behind this optimization? Okay, now function. So we start with functions of one variable. If it is for multi-variable, I think this is for advanced. Okay, so let's start with the one variable first. So now you know that the optimization can be summarized to a function. So mathematically, we can summarize, you can conclude all of the problem in a function, fx. Okay, so now a function, those function that we have, okay, a function now has a local minimum at the value of x naught. If there exists a positive value delta such that x minus x naught less than delta and fx greater or equal to fx naught. In another way, we can write fx naught less or equals to x. Then there exists a neighborhood of x naught here such that for all values for x. So if we want to identify the local minimum, then there exists delta such that x minus x naught less than delta, fx naught less or equals to fx. So that is local minimum. Okay. So in the neighborhood, fx is at least as large as fx naught. So dia sebenarnya macam lebih kurang. Okay. Faham tak? Okay. So that is local minimum. So now, what is global minimum? So fx has a global minimum at x naught if fx greater or equal to fx naught for all values of x. So for global, no need to have any neighborhood. So we don't have to have the positive values of delta. Can you differentiate these two? What is local? What is global? Understand or not? So graphically, we can explain this. Let's say we have here all right, as you can see, which point is the most minimum point? Okay, from here, from A, B, C, and D, which point is the most minimum point?
Point B.
Okay, so this B, graphically, this B is global minimum, the most minimum. But those A, C, and D, we call it as a what?
Local minimum.
Local minimum. Why they are all local? Because there exists at least a positive value of delta such that x minus x naught less than delta. So where is delta actually? The difference between the global here. The difference between here. Different point here. Understand or not? So that fx greater than fx naught. So that is the difference between local and global minimum. Okay, for example, let's say we have fx equals to modulus of x squared minus 4. Okay, so graphically, we have x squared minus 4, so 4, and then this is modulus. Right, so this is the graph. Okay, so basically, you know that this minus 2 and 2 here are global minimizer. We call it as global minimizer. But 4 here can either be local minimum or maximum because we don't know the characteristic of 4 yet. So as you can see, 4 can either be maximum or minimum. But for this graph, is it minimum or maximum? Is there any maximum point along the function?
No.
Then it is
Local minimum.
local maximize. Okay, because we don't know this line stop at which point, right? Okay, that is the difference between local and global. Okay, clear everyone? Anyone has question? Any question? So if the inequalities are reversed, this one, then that is the definition of local maximum and global maximum. Okay, clear? All right, so that is the definition of local and global extremizer. Okay, local or global extremizer, where this extremizer can either be minimizer or maximizer. Right. So now, let's take a look at this theorem. The necessary condition for fx has a maximum and minimum at x equals to x naught, where x naught here is your critical point. So the necessary condition for fx has a maximum at minimum at x naught at critical point is f prime equals to 0. Otherwise, or else f prime is undefined. Right? So if fx naught is undefined, then x naught is not a critical point. So senangnya necessary condition fx has a maximum and minimum at critical point when f prime x naught equals to 0. So the critical point is obtained when f prime x naught equals to 0. Okay, so now let's try this. We have your function. Okay, try to find f prime x here. What is your f prime x here? differentiate this. Okay, one. What is your f prime x here? Can anyone give me the answer?
Doctor, EX over X minus 2 square
X over x minus 2 square. Okay.
minus 2EX over X minus 2 cube.
Ex over sekali.
EX over X minus 2 square minus 2EX over X over 2 cube.
Is it right? Okay, check it. So you differentiate fx and then you get f prime. And then what you need to do is to find the critical point, where the critical point can be obtained when f prime equals to 0. Okay, so for my case, f prime x equals to exponent x minus 4 over x minus 2 cube. So it is just a factorization process here. Then we equal this f prime equals to 0. So we have x equals to 4. So now, by looking at the definition, you know that this x equals to 4 is your critical point, because when f prime 4, then you just substitute x with 4 here, it is equals to 0. Okay, so this is how you obtain the critical point. Okay, but if you use this x equals to 2, f prime 2, it is point. So this 2 here is not a critical point. Okay. So let's look at remark here. So local extremizer happens at the critical point, but not all critical points are local extremizer. Okay, maybe after we obtain the critical point, those are all extremizer. Okay, but after some certain tests, we can identify not all critical points are local extremizer. All right, understand or not? So this is how we find the critical point. Okay, and then these are the example. You can find the critical point. Just find f prime x, equate them to 0, and then you can obtain the critical points. Okay, easy. Okay, then we have the last one here. We have, let's say we have a function of fx, okay, and if f double prime x naught equals to 0, now we have second derivative, or if f double prime x naught does not exist, then if the value of f double prime change sign when passing through the critical point, then we call it as a point of reflection. Okay, clear now? Inflection, sorry, this one. When the sign change from the positive to negative, then the point here we call it as points of inflection. All right, clear?
Clear, doctor.
So a function f is said to have an absolute maximum. Okay, this is for absolute global. Function f is said to have an absolute maximum at x naught if fx naught greater than fx for all x in the domain f, and a function f is said to have absolute minimum at x naught if fx naught less or equals to fx. So this definition is the same as the definition of global here. Okay, minimum fx naught less than fx, absolute minimum maximum fx naught greater than fx. So same. All right, so by theorem 1.3, we have if fx and its derivative are continuous, then x naught is an extreme number if and only if n is even, where n is the order of the first non-vanishing derivative at x naught. If f and x naught less than 0, x naught give a maximum. If f and x naught greater than 0, x naught give a minimum. If n is odd, x naught is not an extreme number. So this one is quite same with the definition of this. We have f prime x equals to 0. We obtain critical. Okay, and then what if your f double prime equals to 0? Here, if f double prime equals to 0 and it change when passing through the x naught, okay, there is a condition change when passing through the x naught. We have a change sign, then we have inflection point. Okay, and then for this case, if f, let's say if f double prime less than 0, then we have maximum. If f double prime greater than 0, then we have minimum. If n is odd, then x naught is not an extreme number. So we don't test for f triple prime. Maybe we can use f quadruple prime. So remember, this n is to be even, okay, to test the extreme number, where the extreme number is extremizer. Clear or not? So now we have f prime. To find the critical, f double prime can either be equals to 0 for inflection, but you need to check the sign changing, and f double prime less than 0, f double prime greater than 0, then what happened to the extremizer? All right, clear? Clear, everyone? Okay, so I think by using the definition, which is quite easy, we just have to find f prime, f double prime, check the sign, so on. You can use the definition to check the example here. It's just to determine the local maximum or minimum, or you can find the inflection if there is change in signs after it passing through the critical points. Okay, clear or not? All right, so that's it for this 1 hour. So now you know the basic idea of optimization, and then the definition of the extremizer. It can be either minimizer or maximizer. Okay, everything's good, everyone?